In class today, we are going to take a couple more steps forward in our conversation around the Rankine cycle. And we're going to do that by solving two example problems. The second one really is just a repeat of the first problem, but now we're going to lift some of the assumptions about the turbine and the pump. For example, that they're not adiabatic and reversible. And so we'll have to start taking efficiency into consideration. And so our first example today asks us to find the efficiency of a steam-driven power plant where the turbine is designed to operate adiabatically and reversibly with an input of 525 degrees C, 9 megapascals, and exhaust the steam at 19.92 kilopascals. Also, to generate 10 megawatts of power, what flow rate of steam would we need? Okay, so to solve this problem, we're going to try to do the same thing that we talked about in the last lecture, where we're going to try to figure out where we are on this TS diagram for each of the operating conditions, and then we're going to try to find the enthalpy and in some cases the entropy at those operating points, and that's going to help us sort of step through this problem and to solve it. Okay, so the information that we're given in the problem is essentially the inlet temperature and pressure for the turbine, right? We've called that point B on our TS diagram before, which you'll see is blank so far. And then the exhaust pressure is 19.92 kilopascals. Now, the thing that we know about each of these stages is that the PV diagram for the Rankine cycle is horizontal in two locations. So the step from C to D is also done at constant pressure. And then A to B is also done at constant pressure. So just from the problem statement itself, we know that the pressure here is 19.92 kilopascals. And we know that the pressure in state A is 9,000 kilopascals. And in this cycle, state D is usually saturated liquid. So we know that we're going to be about here for state D. We should be right on that line. And so we also then are going to have to take the pump work into consideration. So we know we're going to be, it's adiabatic and reversible in this particular problem. So that's done at constant entropy. So that line goes straight up. And then we're there for point A. And then we have to find out where we are for points B and point C. We do know that point B will be out here somewhere. But the thing is that we don't know where C is yet, right? It can be anywhere in this range. So all we know is that from B to C that we'll have a vertical line. And so we know that in the turbine, which takes us from point B to point C, that it is isentropic, right? Because we said it's adiabatic and reversible. So the next thing that I did was go to the steam tables and say, well, if I need to take that step from B to C and I know it's isentropic, let's have a look at what the entropy is at that stage. So from the steam tables, the entropy at point B was 6.7388 kilojoules per kilogram. And so while I was there, I also took the enthalpy because we know we're going to need that to solve the problem. So it was 3,448.7 kilojoules per kilogram from the steam tables. Okay. And so now we know that the entropy in stage C has to be this exact same value, right? And so now the question that we have to try to answer here is, at this exhaust pressure of 19.92 kilopascals, can we find, or where do we find on the steam tables, an entropy value that is just a little bit lower than this number that we know we have to satisfy, and one that's just a little bit above? And the only way that we can do that is actually at saturation. And so if you look in the steam tables, at 60 degrees C, the saturation pressure is 19.92 kilopascals. And the entropy of the liquid is equal to 0.8310, and the entropy of saturated vapor is equal to 7.9108. And so because the entropy value that we're looking for is between these two, we're going to have to interpolate between them, okay? And we're going to do that to find the fraction that is in the vapor phase. Now, while we're in the steam tables and we know we're going to need them, we might as well grab the saturated liquid and saturated vapor enthalpies as well. So the saturated liquid enthalpy is 251.1, and the saturated vapor enthalpy is 2609.7. Of course, that's kilojoules per kilogram for both of those, okay? Now, one of the things that we do know, if you remember, is that state D is saturated liquid. So this is also the enthalpy at state D, all right? And so we'll write that in the table. So we know that this is going to be 251.1 kilojoules per kilogram. We also can write the entropy value because we have it, although we will not use it, okay? All right, so we're starting to fill out this table. Now, to find the enthalpy at state C, which is really the thing that we're after, we need to find the fraction. So the entropy at B, we know, has to be equal to the fraction of water that's in the vapor phase times the enthalpy of saturated vapor plus the fraction in the liquid phase, which of course is just 1 minus the fraction in the vapor phase of the enthalpy of the liquid. Oh, sorry. Entropies, right? Not enthalpies. We'll get to enthalpies in a minute. Sorry about that, guys. Okay, hopefully this makes a little bit more sense. And we can do the same math that we've done a couple of times now, and we can actually solve for the fraction that's in the vapor phase. And of course, that's just equal to the entropy at B minus the saturated liquid entropy divided by the entropy of the vapor phase minus the entropy of the liquid. And we can insert these values that we have. So we know the entropy at B from the table above is 6.7388, and then that's minus 0.8310 divided by the entropy of the vapor phase, which is saturated vapor, minus 0.8310. And that equals 0.8345. So about 83.5% is in the gas phase. And what that tells us is that we're in between here somewhere, right? And probably something like right about there. So if we were going to draw this, right, we're here. And remember that our turbine is adiabatic and reversible, so it's also isentropic. So we're probably something like this, B to C, and then A, remember, comes up, changes phase, and then comes here. And so the TS diagram for our Rankine cycle looks kind of like this. And remember, to calculate the efficiency of the cycle, one of the things that we need to do is find the enthalpy at each one of these points. So we have the enthalpy at points B and D. So now let's find the enthalpy at points A and C. And we can find the enthalpy at C because we know the fraction, right? And here, if I might just fix that, right? That should actually be the enthalpy at C, and maybe I'll do this. The enthalpy at B we knew was equal to the entropy at B was equal to entropy at C, just to be very clear about what we did. So now we need to find the enthalpy at state C. And so that enthalpy value is then just equal to the fraction in the vapor phase times the enthalpy of the saturated vapor plus the fraction in the liquid phase times the enthalpy of the saturated liquid. And so that is equal to 0.8345 times the enthalpy of the vapor phase, which is 2609.7 kilojoules per kilogram, plus 1 minus 0.8345 times 251.1 kilojoules per kilogram. Okay, and so we can find the enthalpy at C is then equal to 2219.3 kilojoules per kilogram. Okay, and what I'm going to do is, since I'm keeping this table, which I do for Rankine problems to just kind of keep everything organized, I'm going to fill in the table. Okay, so this is 2219.3 kilojoules per kilogram. All right, and so now that only leaves the enthalpy of state A to be solved for. Okay, so if you remember from the last lecture that delta H for stage 4, which was D to A, that's the pumping step, right? So that equals delta H of the pump, and that equals the specific volume, which we've said is approximately equal to a constant, times the increase in the pressure. And so from there, right, we know that this is equal to, if I look at the steam tables, we'll assume that the specific volume is approximately 1.017 cubic centimeters per gram. And then the change in the pressure is, let's see, it's 9,000 kilopascals, right? Or 9 times 10 to the 6th pascals. So I can do a simple unit conversion here to change centimeter cube per gram into meters, right? So I can do 100 meters, or sorry, 1 meter over 100 centimeters, not 100 meters, sorry about that, over 100 centimeters cubed. And that tells me that delta H of the pump is 9.153 joules per gram, which of course is just equal to 9.153 kilojoules per kilogram. And I'm going to do that just so we stay in the same units for everything that we're doing. So we can kind of do two things from here. The first thing that we can do is fill in something in the bottom table that I have for the first time, where we have delta H for these various processes. So this is 9.153, right? And of course, that's just work. And the other thing that we can do is find the enthalpy at A if we want to, right? And that's just 251.1 plus 9.153. So that enthalpy would be 260.3 kilojoules per kilogram. Okay. All right. So what we've done is solve for the enthalpy at each point in the Rankine cycle. Okay. And so that means that we should be able to find the heat that's added in the boiler, the work that comes out of the turbine, and the heat that's removed from the condenser. And so if you look at the numbers in the tables or in the table above, well, in the boiler, we're only adding heat. So, right, delta H is equal to Q, just like it was in the previous lecture. And so delta H is the enthalpy at B, which is 3448.7 minus the enthalpy at A, which is 260.3. And so for the boiler, we can calculate delta H, which is 3207 kilojoules per kilogram. and it's the same thing as Q, right? And for the turbine, the work that comes out of the turbine, because it's adiabatic, is equal to delta H. And so the change in the enthalpy from B to C is just 2219.3 minus 3448.7. And so that's minus 1229 kilojoules per kilogram. And then finally, for the condenser, we know that no work is done. So Q is equal to delta H. And so we're going to take the enthalpy at D, which is 251.1, and subtract the enthalpy at C, which is 2219.3. And that's minus 1968 kilojoules per kilogram. Okay. All right. Before I do anything else, does anybody have questions about how we got to here?
Yeah, I have a quick question.
Sure.
So does the quality of saturated steam at C have any bearing over the quality, I guess, amount of vapor at D? Or do we just always assume it's pure liquid?
So you will almost always condense to the pure liquid. In fact, you don't want to pump vapor ever. So one of the things that's often done in these cycles is that it's not always taken only to saturation. Sometimes you'll see it actually subcooled a little bit, just to make sure that the pump doesn't see any gas. But the condition at C doesn't really have any bearing over the condition at D. D is a design point, and whether you choose to make it saturated or subcooled just a little bit just depends on what it is you're trying to do. So that, even though that defines the heat that has to be removed, where you end up at C doesn't have any influence over D.
Okay, gotcha.
Okay.
Thank you.
Yeah, good question. All right. So now that we've calculated the enthalpies and the changes in the enthalpy at each stage, we can calculate two things that the problem asked for originally. The first one is the efficiency, and the second one is the flow rate of water that's required to power a 10 megawatt plant. So let's do that. If you remember, our efficiency for almost everything has been minus the net amount of work that's done divided by the heat that we add to the system. And so in the Rankine cycle, right, you add work or you get work in stage 2, and you do work as pumping work in step 4, and you only add heat in step 1, right, in the boiler. And so, this is really then minus the work that you get out of the turbine, which is minus 1229 kilojoules per kilogram, plus the pump work, which was 9.153 kilojoules per kilogram, and then divided by the heat that was added in step 1, which was 3207 kilojoules per kilogram. And so from here, we can find that the efficiency for this process is 38%. Okay. All right, so there's the efficiency. The last thing that we're asked to solve for here is the flow rate. And remember that the work for the turbine was equal to m dot delta H. And so we can solve for the mass flow rate by the turbine work, right? Because that's where the power is being generated, divided by the change in the enthalpy through the turbine, right? Which is in stage 2. And so that equals, remember, this is minus 10 megawatts or 10,000 kilojoules per second divided by negative 1229 kilojoules per kilogram. And so to generate 10,000 kilojoules per second, or a megawatt, the flow rate of steam that you need is equal to 8.1 kilograms per second. Which, believe it or not, is a huge number. I mean, 8 kilograms a second. If you want to think, there's 3,600 kilograms in an hour. So you are literally talking about tens of thousands of kilograms an hour that need to be moved and pumped. So the pump to do this would be enormous. So would the turbine, in fact. Okay. All right. Before we do anything else, before we try to do anything else, does anybody have any questions about the process that we followed, or the last couple of calculations that we did? All right, I'm not hearing any, but one of the things I want to maybe emphasize to you guys as you're solving some of these Rankine cycle problems is to make tables like this for yourself. It really does help to track where you are. And you'll notice in the first table above, I didn't even fill out every block, right? Because you don't end up needing to know the entropy at state A, even though you know it's the same as state D in this problem. The temperatures don't really come into play except the inlet temperature for B, even though we know both state C and D are at 60 degrees. So I would encourage you, in order to help keep yourselves organized as you solve these problems for the first time, make a table. And that way you know what you've calculated and what you still need to do as you solve these problems. Okay. Now, this again is a pretty idealized version of the Rankine cycle, because we assumed that steps 2, the turbine step, and step 4, the pumping step, were all done isentropically, right? They're adiabatic and reversible. So what happens if we lift those assumptions and make the problem slightly more realistic? So if the turbine is instead being operated at 75% efficiency and the pump being operated at 60% efficiency, how would this change our calculation? And so this is what we're going to do. We're going to solve the exact same problem that we solved just a minute ago, except now we will lift this assumption that they're reversible and adiabatic. Okay? All right. So if you remember, in the previous problem, we had our TS diagram, right? And remember, it was already asked about D, because we sort of have to ask ourselves, what is going to change in a problem like this? Well, in the previous problem, we knew that we were at D, A, B, and C, right? This is what our TS diagram looked like. Well, if we start to lift the assumptions about the processes here and here being isentropic, well, what's going to happen? Actually, this point A is going to come in a little bit, because the entropy should increase if it's not adiabatic and reversible. And also, this should start to move this way. Now, we don't know at the beginning, are we going to be in here still? Are we going to be out here somewhere? We don't necessarily know that at the beginning. But I think it's important for us to think about maybe where we're going to end up on the TS diagram, and how we can use some of the things we've done before in the semester to solve a problem like this. Okay, so to do that, we're going to insert some of the information that we already know. So first of all, we still have the same design points here. So at A, we still need to get up to 9,000 kilopascals. And at D, we're at 19.92 kilopascals. So that's not going to change. They're still done isobarically. We also know that D is still going to exist at the exact same place that it existed the last time. And fortunately, that means that we know the enthalpy there, right? It's saturated liquid. So that's 251.1 kilojoules per kilogram. All right. Now, as we look at this problem, you can start to figure out what the enthalpy is at those different stages. So let's do this first. So we knew this is B, and the state at B hasn't changed. So we still know also that B is 3448.7. Okay. So now our challenge is to figure out where is A in terms of the enthalpy and where is C in terms of the enthalpy. So which one would you guys like to do first? Would you like to do the pump first, or would you like to do the turbine first? Okay, we'll do the pump first. That's totally fine. Then the pump is going to give us A, which, as we said, we know the entropy is going to come in a little bit here. So we know A will be there. But now let's figure out what the enthalpy at A is. Well, remember, for the pump, that the reversible adiabatic work, right? So we have delta H when delta S is equal to 0 equals the specific volume times the change in the pressure. And fortunately, we already calculated that, right? In the previous example, we calculated that that was equal to 9.153 kilojoules per kilogram. Because just like when we were solving problems several lectures ago with turbines and compressors, we're always going to solve the isentropic case first when you're given the efficiency. So we do that here also for the pump. Well, the efficiency for a pump is actually equal to the actual enthalpy that you get out divided by the isentropic case, right? Because the isentropic case is, actually, I apologize for that. It's the isentropic case over the real case, right? Because the isentropic case has the least amount of work that you could ever do. So that means that for the pump, delta H real is just equal to delta H when delta S is equal to 0 divided by the pump efficiency. So that's, in this problem, equal to 9.153. And we were told in the problem that the pump efficiency was 60%. So that's 0.60. And so delta H for the pump then is 15.25 kilojoules per kilogram. Okay? And remember that delta H for the pump just equals the enthalpy at A minus the enthalpy at D. And so if we're interested in the enthalpy at A, that's the enthalpy at D plus delta H for the pump, right? And that's equal to 251.1 plus 15.25 kilojoules per kilogram. And so the enthalpy at A then is just equal to 266.3 kilojoules per kilogram. And we can add that to our table. So 266.3 kilojoules per kilogram. Okay. So is that okay with everybody? Does that make sense?
Yes.
All right, good. All right. So now we've mostly filled in where we should be on this diagram. So now we have to do the same thing for the turbine. And remember, when we would work on turbine problems in isolation, the very first thing that we would do is solve the isentropic case. And we did that because our relationship in the turbine was actually very, very similar to the one that we have above for the pump. So for the turbine, the efficiency of the turbine was equal to what? Which direction was it? Anybody?
It would be real over isentropic. Is that what you're asking for?
Yeah, exactly. Thank you.
Oh, okay.
Delta H when delta S is equal to 0. Well, here, right, we're after the real enthalpy of the turbine. And so that's just the efficiency of the turbine times delta H when delta S is equal to 0. So that's 0.75 in this problem times the isentropic enthalpy, which we already did in the previous problem, right? We already solved the isentropic case, and that was minus 1,229 kilojoules per kilogram. And so then delta H real for the turbine is equal to minus 922 kilojoules per kilogram. And so that means that the enthalpy at C, if we want to fill out the table, right, of course, it's just HB plus delta H real for the turbine. And that's 3448.7 plus a negative 922, which is 2527 kilojoules per kilogram. So if we fill this in the table, right, we know that the enthalpy at C is 2527 kilojoules per kilogram. Now we don't quite know where point C is on the TS diagram. And here I'm gonna do this so if people are still writing, they can catch up. So we need to figure out, are we saturated vapor? Are we subsaturated, right? Or do we have a quality that's less than 1, right? And the answer to that can come from the values that we looked up in the previous problem. So remember that the enthalpy for saturated liquid was equal to 251.1, and the enthalpy for saturated vapor was equal to 2609.7. And so you'll see the enthalpy at C at the same pressure is lower than that number. And so that actually tells us that we're still in here. Okay. So we're right in here. And so that goes that way. And this actually angles out just a little bit, right? And we could calculate what X is in this particular problem, right? Because we know that the enthalpy at C equals the fraction that's vapor times the enthalpy of saturated vapor plus 1 minus the fraction times the enthalpy of the liquid. And so we could do the same thing that we've done before, where we reorganize this, and that fraction is just the enthalpy at C minus the enthalpy of the liquid minus the enthalpy of the vapor minus the enthalpy of the liquid. And you plug all of those in, and the quality in this particular problem is equal to 0.96, right? So 96% of the water coming out of the turbine is in the vapor phase, okay? And now in this problem, right, we have the enthalpy at all 4 stages. And actually some of these steps, we already have delta H. So we can solve for both the efficiency and the mass flow rate, right? And the efficiency, we'll use the exact same equation that we used before, where it's still minus the net amount of work over the heat that we added. And that's equal to minus, right, delta H for the pump plus delta H of the turbine, right? And that's real, right? These are both real, divided by the heat that we added in the boiler. So that's the enthalpy of B minus the enthalpy of A, because I didn't calculate Q boiler directly here. And that's equal to minus, this was 15.25 when we did that calculation. And this was minus 922 kilojoules per kilogram, divided by, then the enthalpy at B was 3448.7 minus 266.3. And of course, all of those are in kilojoules per kilogram. And that gives us an efficiency equal to 28%. And so the efficiency here is much lower than when we assume the pump and the turbine were adiabatic and reversible. In fact, we've gone down by 10% efficiency, or we've really lost about 70% of, we've lost about 30% of our operating efficiency. And you can see that most of the reason for that is the turbine. You know, the pump has an effect, but it's a much more muted effect than the efficiency of the turbine. That's a very important part of the overall process. And we also then can calculate the mass flow rate using the same equation that we did before, right? It was just the work of the pump, which was minus 10,000 kilojoules per second, divided by the work that's coming out of the turbine, or 922 kilojoules per kilogram. And so the mass flow rate now that's needed to generate the same power when we actually take efficiency into consideration is 10.85 kilograms per second, which is about 20% higher than it was in the previous problem. And so the effect here is not only do you get less power out of the overall system, do you lower the efficiency that you have in converting chemical energy from a fuel into mechanical energy, but you also now have to increase the size of other components. So this 10 kilogram per second might require a larger pump than the adiabatic reversible case, or the size of the heat exchanger, which could, like I said, be a river in the last lecture, might need to be larger in order to provide that flow rate. So there are a number of interesting ramifications from a design perspective that occur as the efficiency goes down. Okay. Is this problem okay? Do you guys have any questions about any of the things that we did? If there are no questions, there's one other thing I want to talk about, and that is, how might we be able to increase the thermal efficiency of a process like this? Almost all of the cycles that we've talked about have had efficiencies that are in this 30% range, which quite frankly are typical. So the example problems that we've been solving give fairly realistic estimates of the overall efficiency of converting thermal energy or chemical energy into mechanical energy. And actually, if you think about this, that 30% number should feel very familiar, because we looked at the Lawrence Livermore National Lab plot in one of our previous lectures, and the global energy efficiency is right about that number, right? It's about 33%. So the numbers that we're calculating here are realistic. But there has been a lot of creativity involved in trying to figure out ways that we can take, especially for larger systems like power plants, how we can extract more energy from that system and increase the overall efficiency. So I want to just share two examples with you where I'm going to just share the flow diagrams, but we're not going to do any math. Although this used to be one of my favorite things to give as a project, is one of these next two cases. And one is cogeneration. And really what cogeneration means is that you're trying to produce two things. One is power, and the other one is heat that you'll use somewhere else in your process. Right now, in our Rankine cycle, the turbine effluent goes right to the condenser. But oftentimes the turbine effluent is still pretty warm. In the last example that we did, it wasn't. We let it go all the way down to 60 degrees C. And if you did that, you would effectively have such a low quality heat there, you wouldn't recover that for almost anything. Although, as we talked about in the Stirling engine lecture, that might change someday. But oftentimes the flow out of the turbine is still at a couple hundred degrees. And that can be used to run things like heating systems inside of buildings or houses. And so one of the very common things to do is, if the effluent's coming out of the turbine, to have a heat exchanger between the turbine and the condenser that is going to make steam or hot water. And then that steam or hot water can then be pumped further on down in the process. Okay, so introducing this steam use or heat recovery, the gold box here is one way to increase the overall effectiveness of the process. Okay, so that's one thing that's very commonly done. The other thing that's done is to make, instead of a single cycle, to make something like a combined cycle power plant. And so this figure here actually has two processes that we've talked about in class. So in the top here, there's a Brayton cycle. And in the bottom here is a Rankine cycle. And the way that this is operated is that fuel and air are first fed to the Brayton cycle, where you go through the turbine in the Brayton cycle, right? And so you make the blades spin, that directly generates, goes to a generator, which makes electricity, right? Which is then transmitted somewhere down the line. But leaving a jet engine, the effluent is extremely hot. In fact, when we solved a couple problems related to the Brayton cycle, you're still talking that can be at, hundreds of degrees C. And oftentimes you just let that go into the atmosphere. Well, instead, if you ran a Brayton cycle, one of the things that you could do is use that exhaust as the boiler for a Rankine cycle. And you'll see that's exactly what's happening here. So following the water pump in the Rankine cycle, remember, we pumped to the boiler. And here, that's being pumped in this heat exchanger that is getting heat from the Brayton cycle, or the exhaust from the Brayton cycle. And then it's coming out then at higher temperature and pressure, going to the turbine in the Rankine cycle, which then that comes out. And you even could use cogeneration here. So you actually could input a cogeneration line here if you wanted to, just like we showed on the previous slide, and then send it to the condenser, then back to the pump, and just run this continuously. And if you do this, it's actually not uncommon to have combined cycles that can get efficiencies north of 45%, where you convert the thermal efficiency into electricity through the two generators.